Okay, any questions before I move on? Okay, so last time around we had looked at modeling processor and modeling radio, and and also the displays. And essentially, what we are headed towards is to try to sort of model different aspects of a system in terms of how power relates to performance or energy to the amount of work, and then stitch them together into what an overall system does. But along the way, that kind of also gives us some insight into things that how may play out. So for radio, we had this very simple model, which basically says that look for when it comes to energy for transmitting a bit, there is some sort of a constant term, some sort of a term which relates to the distance. We stitch these things together, and that also leads to insights such as if I'm transmitting over a long distance, then it may be better to transmit over multiple shorter hops because we get advantage. There's a more than a linear advantage in terms of transmitting over a hop, but excuse me, but there is a linear increase in number of number of hops that we have. So it leads to this kind of a critical distance beyond which multi-hop kind of becomes possible. Another aspect we talked about was that it's not simply how much power I'm consuming, but also how much energy I need every time I shut down and restart. So this, in case of radio, takes the form of a radio startup time. So before you can send out a bit, you have to power up the radio, you have to send out some synchronization signals. All of that takes time, and the energy consumed during that is an overhead that gets associated with every bit. So what we see out here is that the energy that has to take into account not simply how much time you transmitted, but also what was the cost associated with the startup. And if you are doing lots of work all the time, startup cost is going to disappear and get amortized. But if you are doing relatively small amount of work occasionally, then this kind of becomes very significant. So for systems which are designed to operate in settings where they're running very sporadically, this startup power kind of matters quite a bit as well. So if we look at a complete system, so what we have out here is sort of some wireless sensor nodes, and what you see is that in these devices you'll have a processor, you'll have a radio, you'll probably have some storage, and all of these things, if you look at each one of these individually, they could be shut down or put to sleep, and when you combine them, then the overall device ends up having many different modes of operation. And there are some interesting sort of differences you would see. So this first one is a very old device. It's the most recent of these devices. So it's making use of a TI microcontroller and one of these so-called Zigbee radios. The middle one is a very old device. It uses a Atmel processor with a sort of a garage door opener type radio. And then Mica Z is kind of in between. It uses a Atmel processor, but the same radio that is kind of used out here, a similar radio out here. So what things stick out for you out here? Like when you look at these different numbers. So here is the whole system, which is on standby, and the real-time clock is on. Another one is that the CPU is idle, but the oscillator is on. CPU is active. CPU is active, and the radio is in reception mode. CPU is active, radio is transmitting. CPU is doing some flash memory read and write, and then finally also the wake-up costs. So looking at this, let's look at the first line, for example, standby. And you see that this Telos device is 5 microamp, whereas these guys are like 4 to 5 times higher. What ramification do you think this will have, this property, that a system which has very low standby power? Any thoughts? Like, in what ways would it help or hurt? Now, since there's so few of you, I don't know what happened to the rest of the class, but if they dropped out, that's great. But you have to speak now. That's the bad part. So.
Could you repeat the question?
Okay, so you were pouring down on it. Okay, so look at the first line, stand by for the whole device. Okay, we see a significant difference between the first device and the latter two. Okay, this guy is like 5 microamp at a lower voltage, so it's 2 times 5, 10 microwatt, whereas this guy is like almost 60 microwatt, and this guy is almost 80 microwatt. Okay, so there's a almost like close to an order of magnitude range out here. My question is that this particular, in what settings do you think the first device would excel because of this property that the standby power is so low? Yeah, so most of the time we are on but doing nothing, right? I mean, this is sort of. Let's look at the next one. So all around you would see that this guy actually excels quite a bit. Okay, idle. Okay, so in this case, so the difference between here and here is in this case the clock is shut off. The only thing which is on is a real-time clock. Real-time clock maintains the time. It's a very slow oscillator, 32 kilohertz usually, and that's all it is doing. The second guy. So here we have a oscillator on, the microcontroller unit is idle, so the processor is essentially idling, it's doing no op instructions. And what you again see out here is that this guy is pretty darn good. It's like 60 microamp, but whereas these guys are into milliamps. Okay, so and these two numbers are the same because the processor here is the same. So this guy kind of excels. Another thing you would notice is that this guy has a lower voltage, 1.8 volt versus 2.7 here. What benefits do you think would accrue from that, from a lower voltage?
Lower temperature?
No. Why do you think?
Power saving.
Okay, I mean there's power saving, but simply because power is voltage time current. But generally speaking, if I operate something at a lower voltage, then the current will go up. Okay, so that power saving tends to be artificial, right? I mean, if I have a resistor, I lower the voltage. Sorry, if I have something consuming whatever 1 watt, if I lower the voltage, the current will have to go up by that time, by that amount. But something more. So these are battery operated devices. Okay, what ramifications would the lower voltage have now? So what decides the voltage of a battery? Actually, what is the voltage of a AA battery?
1.5.
Okay, roughly 1.4, something like that. Okay, are all AA batteries that AA size batteries of that voltage?
Yes.
No. Lithium, if you have lithium batteries, they'll have a different voltage, right? So it depends upon the chemistry of the battery. Okay. Now, let's say I have AA batteries. Okay. Let's say I'm running this thing on 2 So if it's 1.5, clearly I cannot run these things on a single AA battery. Okay. So I have to run it on 2 AA batteries. Now, what happens when a battery dies? Like if you were to look at the voltage of the battery as the battery dies, what happens?
It goes down.
Voltage goes down. Okay. So now this guy is going to die sooner, right? I mean, because as the voltage starts going down, there's a very little margin out here. In fact, AA is more like 1.4 or something, so it actually has a very little margin, whereas this guy can keep going down quite a bit. Okay, so you can extract more battery life out of this because of the lower voltage property. So that's the point. Let's look at this. MCU wake up. 6 microsecond versus 180 microsecond. So this is basically saying that from the time the processor is woken up via some sort of an interrupt. So usually these processors have some instruction saying go to sleep until there is an interrupt. Okay, so kind of the idea is system is put to sleep and then some external event. Okay, in a laptop it might be the keyboard press and all, but in these kind of systems it could be a packet arriving on the radio or a sensor giving a trigger or something like that. So this is 6 microsecond, this is 180 microsecond. Okay, huge difference. And you would also see that the radio is more agile out here as well. The radio from the point you wake up. But let's look at this. So processor waking up 6 microsecond, this is 180 microsecond. Again, in what way would this help us? And clearly lower is better, but what can I do with in this regime that would be harder in these devices? Like as I increase the cost of starting up, what am I hurting? Let's take the extreme case. Let's say some device were to take a minute to start up. How would that affect your decision to put that device to sleep? You don't want to. Okay, so it goes back to kind of the same point which we have out here, which is I wouldn't want to put it to sleep because for it to wake up is going to cost a lot of time and wasted energy, basically. So, so one thing we'll see later is that there's probably going to be some sort of an optimum strategy for us to decide when to put a device to sleep, which will depend in part upon this number, which is how long does it take for me to wake it up. These numbers at all scales of devices have been something which have been a focus of a lot of effort. For example, rapid boot up. I mean, if you just look at your laptops and desktops from maybe just 5 years ago, things used to take a lot of time to wake up and all, and now it's instantaneous wake up. Okay, almost instantaneous. What changed? What do you think made that happen? You know what I'm talking about, right? I mean, with the tablets and all now, I mean, essentially we press a button, it's on. Whereas it used to be like my PC was hibernating or whatever, I press a key and it will leisurely kind of wake up and all. Okay.
Before you had to wait for the hard drive to start spinning up and load everything.
Okay, so flash drives make a difference. What else? No, actually, cache you'll probably have cache being on chip. Will probably, if you're hibernating, then it's probably going to be powered off. So cache will probably not maintain its state. Huh? RAM.
Yeah.
What about it?
Like restore all the previous state to instead of the hard disk.
Right. Yeah. So what do you mean by restore the previous state of the RAM? How?
So that we wake up the system, we can already access the previous.
Right. Yeah. So one big so DRAM is the huge amount of memory, and it used to be that you would have to save all of that into hard drive and restore it. The thing that changed is that they came up with DRAMs which could be put to a lower voltage mode, so that during that lower voltage mode they can preserve the state but are not otherwise functional. Okay, so essentially the need to put dumb stuff into the drive and restore it kind of disappeared, and that was kind of a huge win that happened. So and these things kind of both the transition from hard drive to flash as well as these kind of newer DRAMs which can hibernate, they all kind of happen pretty much simultaneously. So okay. The third area in which made it happen was the operating systems themselves. So there were a lot of things where the boot stage would take a long time. Like, for example, it would examine your USB bus, what all devices are there. A lot of interrogation goes on and all. So it used to be that, I mean, if you look again, booting of operating systems, Linux and all, maybe 5-6 years ago versus now, they on identical machines they have sped up quite significantly, and a big role was that basically it entered into this consciousness that we could do it now, that we could speed things up. There are still a lot of issues out there. Like, for example, I was playing with some National Instruments card, and it had all these instructions about not putting to sleep and all these kind of things. And the reason is the following: that you put the machine to sleep, and then you wake up, and the configuration of the machine has changed. The configuration could change. For example, I had some device plugged in, I removed it while the machine was asleep. So the OS somehow has to be able to recognize it, because so while the memory state can be recovered, the physical state, if it has changed, it has ramifications as well. So, it's a somewhat complicated thing that the OS has to deal with, but nevertheless, kind of boot times have been tremendously kind of improved. What factors do you think come into so this kind of state recovery and all is certainly one aspect. What else do you, in this particular case, these times are actually simply time to execute the time from interrupt to the first instruction. So this is not taking into account any sort of boot time and all. What do you think accounts for like a 6 microsecond number? What is happening in that 6 microsecond? You know what I'm saying, right? I mean, this is interrupt to the first instruction. So not all these other issues that we were talking about are not there. And in this particular device, the memory contents are preserved. Okay, so they are not. We don't need to restore it. Okay, so what all do you think might be responsible for this kind of a number? Restoring state of the register. Yes, that could be, except that I think in this case the state of the registers are also preserved because the registers and the RAM were and the SRAM were one and the same thing basically. Okay, so first thing is when you are waking things up, your voltage needs to stabilize. And the other thing is your clock needs to stabilize. When you turn on the clock, it's not that the clock immediately starts running at the right frequency. Okay, so it kind of takes time. So those are the factors which kind of result in this kind of number. And in fact, people who designed this particular board, they made a big deal that how they optimized their clock startup quite significantly, and that how that was responsible for this kind of huge decrease going out here. So there are all these lower level hardware parts of the system which kind of are often responsible. Same thing happens with radios. Inside the radio you have phase lock loops and things like that, which again take time to stabilize, which often accounts for these kind of larger numbers. So that was kind of a glimpse into some of the models that one can develop. But unfortunately our problem doesn't end there, because these models themselves have a lot of uncertainty. So while we can use these models to make predictions, to do our power management and all, one thing one has to also worry about is that these models are not perfect. Okay, if nothing else, these models depend upon your operating environment. We already I referred to that, how temperature affects the power which is consumed. Okay, and so all those parameters we had, alpha 1, alpha 2 and all, they are actually dependent upon ambient conditions also. But another source of variation is the fact that otherwise identical systems may be using parts which exhibit power variation. So like for example, if you look at, like, let's say you buy a embedded board and it would say you can use any DDR3 memory in it. Okay, so DDR3 is a DRAM specification. So you go on Amazon or Newegg or whatever, and you type DDR3, and you get a DIMM, and you plug it in. Okay, the problem is that I may have identically spec'd parts from different vendors, which are very different in their power profile. So this particular one is showing that. Okay, so that's one, and the second one is. That I may have identical parts, as in same part number, but because of variations in manufacturing, it may exhibit differences. So this first slide is showing that there are 5 identical Intel processors, and this is showing not the absolute but the normalized power. But what's happening out here is part number 1, if we called it 1 unit of power, part 2, 3, 4, 5, they had powers which varied as much as 10%. Okay, so this is under identical operating condition. They are basically exhibiting a spread in power consumption, and the reason behind this is that when these parts are made, there are subtle variations in the sizes of the transistors and stuff like that, or just the chemical processes that are used have variations and all. So some degree of power variation is always there, and in fact this variation has been going up and up and up as technology has been shrinking. Okay, so that's one aspect. Another one is power variation from design. So this was the first one which I was referring to, which is I buy identically spec'd parts, but they are made by different vendors, okay, and therefore they have different circuits or sort of other different details. So in this particular case, this is a study out of IBM. So they bought a bunch of DDR2 parts with identical performance specification, but the difference in power consumption was quite significant. So this left-hand side is active and the right-hand side is idle mode power. And the thing that's kind of interesting is that the variation is between is 2x across these parts. Okay, so you could essentially the underlying design and the and maybe the silicon technology they are using, you know, all of them are kind of adding up. So identical performance, but power consumption is significantly varying. Then we face variations from temperature, from the environmental conditions themselves. So what you see out here is that ambient condition and CPU performance are related. So basically, if I have a drop in ambient temperature, then there is a corresponding drop in CPU temperature, and then that would in turn affect the power consumption. So that variation becomes an issue. So all of that, what it leads to is the following, that when you are dealing with hardware, there are many different ways of analyzing that hardware and kind of commenting upon whether it's something which is efficient or not. Earlier on, I had made a point about that how energy and power are two very different metrics, and how it could be that something is better from an energy perspective but worse from a power perspective. This shows some examples. So what we have out here is looking at some embedded processors, in particular looking at processor out of Atmel and an ARM-based processor. And what you see out here is that this processor, the first one, which is an 8-bit microcontroller, burns 16.5 milliwatt, and the ARM processor burns 75 milliwatt. And if I were to, and this guy is running at 40 megahertz, and this guy is running at 4 megahertz. Now, certainly, just focusing on this number is a little bit misleading now, because they are also very different types of processors. 8-bit versus 16-bit, and 4 megahertz versus 40 megahertz. So very important that one not confuse low power and energy efficiency. So for example, if I look at the first processor, it is 4 nanojoule per instruction, with assumptions like it's a RISC processor, so 1 instruction per clock cycle, and so on and so forth. Or another way of saying it, that it gives me 242 MIPS per watt, 242 million instructions per second per watt. If I look at the ARM processor, it is almost 2x better, okay? And the instructions are not even the same. I mean, clearly it stands to reason that the ARM processor with a 16-bit data path is going to be able to do a lot more work per instruction than this first guy. And that will show when you run some algorithms which kind of make use of that wider bandwidth. Other examples, so this is a range of processors, and what I wanted to show was that the wide diversity of nanojoules per instruction that you see. So this is some obscure company Signal, which makes a Intel 8051 processor, which is very old, one of the very first microcontroller which is out there. What you would notice, it runs very slowly, 32 kilohertz, okay? But it gives an amazingly low nanojoule per instruction. On the other hand, by the time you hit like some of the ARM processors or IBM PowerPC type processors, we are into 1 to 2 nanojoule per territory, so 5 to 10x worse kind of thing. So, and again, in these things, we are not factoring in the operand size difference. So this one is 8-bit processor, whereas these guys are 32-bit processors. So that difference will certainly show up also. So when looking at comparing hardware or comparing systems, one has to kind of look at efficiency in two different ways. One is active mode efficiency. What I mean by that is that when system is running, how efficient it is. So processor, for a processor, it might be sort of power and instruction in different modes. So, and for radio, it might be power, with relationship bits. So, for example, when I'm transmitting at a certain bit per second or doing work at a certain instruction per second, what the power consumptions are. And for sensors, it could be the sampling rate. So this is one way of looking at things. And the other way is sleep mode efficiency. And what I mean by that is what is happening while I'm asleep and how long it takes me to come out of sleep. So those two parameters we saw earlier, idle power consumption in idle or sleep mode, and how much it takes. One thing you will notice is that you'll see in realistic processors and all is that they have many of these sleep modes also. Idle mode, sleep mode, deep sleep mode. They will have names like dozing mode and things like that. And what they differ in is, in all of them, the basic processor functionality, the processor is not running or the radio is not transmitting, but what state is preserved and how long it takes me to come out of it. So like it could be a minimal mode where processor's clock is up, registers retain their value, and if you want to start, you basically start in 0 time. To another extreme where processor is powered down, the registers have lost their value, clock is not running, and so to wake up, everything needs to be done, and various things in between. So for any given application, you are going to have some fraction of the time where the processor or the system is going to be in sleep, and that is going to depend upon the application. So for example, if I have a device which every time someone passes by, wakes up, captures an image, processes the image, perhaps tries to detect the face and do something, versus something which is always monitoring a crowd or something like that, they are going to behave very differently, and they will stress these two dimensions differently. In the latter case, where individuals are passing by once in a blue moon, this may dominate because most of the time you may actually be spending in the sleep mode, and therefore optimizing for that becomes important. Whereas if, on the other hand, you have something which is always running and all, then the active mode is going to be important. And the cost of transitioning between becomes a very important metric also. So sleep to active transition, and also active to sleep. Do you think active to sleep will take time? So sleep to active, we saw that takes time for a variety of reasons. What about sleep? What about active to sleep? What kind of things would one need to do when shutting down? Save state, okay. So if it falls, if my DRAM didn't have the low power mode and all, I have to dump it to the hard drive and all those kind of things. So saving state is one. What else?
Turning off the clock.
Yeah, that would be pretty quick actually. Sure. Yeah. Well, actually, I mean, but that's almost. What else? I mean, let's say you're shutting down this building or shutting down a car. Right? What kind of considerations will come in there? Let's take a smart home which received the signal from the utility to cut down the power. Can you just shut off the microwave oven, let's say, or the dishwasher or things like that? You need to like wait for them to be in a safe state of some form, right? I mean, not everything is shuttable depending upon the state, so something critical may be going on. So you have to generally bring the system into a safer state before you kind of initiate the shutdown. So sort of going in the reverse direction can also have these costs. And next few slides kind of show how these things kind of play out. So what you have out here are two embedded systems. One is a high-end running a 32-bit type processor, and the other is a 8-bit type thing. These are somewhat old, roughly 10-year-old devices. So that's what I had to put in data. So first thing to bring out is that this second device, by any stretch, is a lower power device. This is milliwatts. This is watts. Okay, so almost more than 2 order of magnitude difference between the two if you were to just look at the power numbers. But when you look at them in a realistic application setting, things look very different. So in each one of these upper 3 plots, the right bar is when it is running on the high-end processor, and the left one is when it is running on the low-end processor. And the y-axis is the energy. So remember, The right one corresponds to the so-called higher power platform. The left one is for the low power platform, but from an energy perspective, the picture is dramatically different than that to the log scale. And what we are seeing out here is that for bulk processing, the architectural efficiency of the processor ends up dominating the fact that you had a lower power design, lower power circuit. So just focusing on the power number can be very, very misleading. The bottom plots are showing showing how the second form of efficiency that we talked about, the sleep mode efficiency, kind of plays out. Okay, so in particular the wake up time. So what you see out here is this is the higher power device, and when it is suspended and then it's woken, so to suspend it and to wake it up. Okay, so what's happening out here is these are some interesting numbers out here. So to resume this performance, resume this thing, it takes around 11 milliseconds to boot up, and during which it consumes around 4 millijoules. And while it is asleep, it consumes around 20 milliwatt. Okay, so by any stretch, these are by comparison with our laptops and all, these are pretty impressive numbers. Okay, just 10 milliseconds to wake up, 20 milliwatt while asleep. Okay, so pretty good. But when you compare it against the low power device, this guy takes 4 milliseconds to boot up, consumes only 7 microjoule of energy while waking up, and during sleep mode it consumes microwatt. Okay, so clearly if I have tasks where I need to spend long periods of time in sleep, wake them up frequently, it's better strategy to let this guy do that kind of work and put this guy to total power shutdown. On the other hand, if I'm doing active work, it's clear from the first one that I'm better off actually doing bulk computation on the big guy. Okay. So how do you think you can combine, how can you create a system which can combine properties of both? Right? I mean, for bulk computation, the Stargate is the big ARM processor is doing better, whereas for this rapid wake up, sleep, and all, the mode is doing better. So can you how would you combine these two complementary properties into a single system, Jeremy?
Have 2 cores.
Okay, and then yeah, you're on the right track. So
You switch the task from one to the other.
right. So kind of the concept is the big core is powered off. Okay, not simply suspended because it consumes tens of milliwatts there. It's powered off, and then whenever we need it, we wake it up and transfer the stuff to it. But otherwise, kind of this rapid wake up and all is happening on the small guy. So we always are kind of on the lookout for that. Should I wake the big core up? Okay, and if we don't do it, then we take a computation hit, and we may actually come out worse also in terms of energy, because so you want to make things up. So depending upon the workload on the system. So these kind of concepts used to be somewhat esoteric, but then in recent years, ARM came up with a concept called big.little. Anyone heard of it? Big.little. Okay. I think I might have talked about it in 202A also, but basic concept being that there are 2 processors, a big processor, a little processor, and now phones have it. So the newer Samsung S6 devices, for example, have 4 big processors, 4 little processors, and kind of the idea is that you keep moving. You can think of it as 4 clusters of big little. Okay, so each pair has a big little pair, and then you kind of transition tasks between them. And so when the workload starts becoming too much for the small processor, you pick up the big processor. That's kind of conceptually the idea. So this same aspect of active mode energy versus power management efficiency you see in the radios also. So this chart, some of these rows we had seen before. This cellular radio, Wi-Fi radio, Zigbee radio, and a Bluetooth radio. So that's the upper few rows we had seen before. The thing I want to bring out is that if you look at the sleep mode, idle mode and sleep mode number, and then startup time. So if you recall, Wi-Fi had looked very appealing because its active mode energy was terrific, 15 nanojoule per bit, whereas even our Bluetooth was several factors worse. But if you now look at idle mode power, the Wi-Fi device is 400 milliwatt of idle power, whereas Bluetooth is 6 milliwatt of idle power. And if you look at sleep mode power, I didn't have the number for this, but this guy is less than a milliwatt. And in terms of startup time, this guy takes order of seconds, and this guy tends to be better, okay? Whereas these devices, these Zigbee devices are in milliseconds, okay? So a couple of things which are happening. Firstly, the Wi-Fi devices are complicated devices, okay? Just in terms of how many transistors they have. All this high-speed stuff comes because the electronics are more complicated. So they have lots of leakage power, okay? Good old equation. So that's why the idle power is much higher. Whereas Bluetooth radios are very simple radios. Fewer transistors and all, so that's the effect what you are seeing. These Zigbee radios were actually, interestingly, explicitly designed to be rapid to wake up. So one of the screw-ups, if you may, that Bluetooth made early on, so Bluetooth was positioned as a low-power device, but it was a bit of a design by a committee. So what ended up happening was, while it is low power in the sense of when it is active, it consumes less power, and it was mostly an artifact of that the rates were lower, data rates were lower than Wi-Fi, and the other thing is the range were lower, like tens of meters versus hundreds of meters, and order of few hundred kilobit per second to a megabit per second versus tens of megabit per second. So Bluetooth was being positioned as a low power device, but the mistake they made was they made the synchronization it has to do upon wake up tremendously complicated. Anyone knows how Bluetooth works? Like how does it? I'm not talking about the newer Bluetooth LE, this sort of a good old Bluetooth. When it needs to communicate with your laptop or your phone, like what happens? How does it conceptually work? Right, so there is a handshake process which sort of goes on, and the other thing is Bluetooth works based upon what is called as frequency hopping. Huh? Frequency hopping. Okay, so it has to synchronize also. So there's a upfront process which needs to take place essentially to establish a connection, and all of that can take quite a bit of time. Okay, which is why you would perceptibly notice that it takes significant pairing time. It's not instantaneous. Whereas, so one of the things that these folks in the Zigbee, they actually by that time, so Bluetooth has been around for a while now, right? The Zigbee came into being a few years later, and by that time the consciousness has set in. So they explicitly went around doing a few things. One of which was they wanted to make sure that idle power was less, which is it can be whatever sleep mode power was less. So you can see that 0.03 milliwatt versus 0.8 milliwatt. Okay. Another thing is they really designed it for a rapid wake up. Okay, so that's a more of a protocol level issue, which is why you see milliseconds out here versus seconds out there. So now, since then, of course, the landscape has changed quite a bit as sensors became very prominent, and also now we have this Bluetooth LE, which sort of went after kind of this territory, sort of. In the sense that sensors talking to phones. So for a while there was this debate that could it be that we'll have phones with Zigbee radios, okay? And people tried all sort of things, putting Zigbee radios inside and all. There was another radio standard called ANT, or not a standard, but a popular radio format called ANT, which was a private standard, but it is very common even now among. Like if you go to the gym, your treadmills and all, when they have wireless chest straps and all talking to the thing, they use these ANT radios or ANT++ radios, and they also had similar characteristic: very rapid wake up, very low power sleep mode, very low power active mode. So BTLE is basically took that territory, and it has some very interesting characteristics now in terms of very rapidly it can send a message without an elaborate sort of time. So this portion, these two numbers have been improved tremendously. So what all of this translates into is perhaps something that an observation, and I think it maybe says something about the nature of the technology, which is devices which tend to be good in active mode efficiency tend to be the one which are bad at power management efficiency, and vice versa. So bulk processing efficiency of that, and sort of this rapid wake up, they seem to be at odds. We see it in CPUs, so small thing, big thing. You see that the small stuff does worse when it comes to active mode power consumption, but they are pretty good when it comes to starting up or sleep mode power. And we see the same thing in radios, and you'll actually, generally speaking, see it in a lot of things. Essentially, what is happening is that for the big stuff gets its energy per unit of work efficiency because they throw architectural features at it. Okay, but that comes at a cost because there's more hardware and therefore more overhead, more wastage. So another good example would be like if you look at like a modern higher end processor. Okay, they do all sort of tricks like lots of cache, for example. They may have out of order execution of instructions. So instructions, if an instruction which is out in the future can be executed because it doesn't have any data dependency, they will do that. They have multiple hardware units which may lie idle, but they're gaining speed. So these things end up overall winning out when it comes to energy per bit. But all that stuff increases idle power, and it also is a more complicated device, so it has more state, and so saving that state and restoring that state takes more time. So this is perhaps at some level inevitable. Small things are more agile, but when faced with heavy duty tasks, they are less efficient, and we see that again and again. Okay, so that was the story insofar as modeling is concerned. I'm going to assign some papers which will touch upon this modeling for some other aspects of the systems, but for now we are going to move to another aspect of the system which is very important, which is batteries. So batteries play a couple of roles, and they are sort of distinct from each other, but nevertheless worth pointing out. So one is they are the primary source of energy for untethered systems. Okay, so our phones and stuff like that. And the other is that they are storage to cope with intermittent availability of energy. Okay, so in the first case, they are the only source. I mean, in the other case, there is some other source, except that source is flaky, intermittent, and therefore battery acts as a buffer to even things out. There can be other reasons why we might also use battery. Can you think of some? So here, this is the mobile phone. This one is, let's imagine I have a device which works with, I don't know, like a harvest energy from light or my walking or whatever, and then I have battery being used to even things out. Okay. Can you think of other uses of energy, other uses of battery, other ways batteries are used?
Like my desktop computer might have the backup battery in case the power dies.
Okay, so to preserve state while I'm powered off, I guess is what you are saying, right? I'm disconnected.
It's the ones like you have power outage.
Yeah, I guess it falls into this category, right? But, okay, what else? So,
Are you looking for something that's not in the two categories?
of course. So another use I've seen in some papers now in recent years is as a privacy entity. So kind of the idea is that people who do not want the utility company to be snooping on them. So what happens is that your power consumption at the home, the smart meter readings which are going out. So from the power trace, utility company can tell a lot about what's happening at your home. So what you can now do is to have a battery pack at home and then essentially even out the power trace, okay, to kind of make things more effective. Of course, there's a cost associated with it, needless to say, but so that's another use that I have seen. There are other reasons also. So here I said storage to cope with intermittency, which has implication that energy is not available at the right time. But it also could be that energy is available, but it's not the right price. So what I mean by that is that I can store energy when the energy price is cheap and then use it later on. Okay, of course, it will have a cost issue, which is I have to take into account the fact that I have to buy the battery, and then every time I discharge it, the battery is going to age. So I have to factor those things in. But you could imagine that battery can be used to, we can use to charge it up late at night when energy prices are low, and then use it when prices are high. We don't get to see it currently because our energy prices at homes at least do not change with time, but for bigger electricity users and all, that is certainly the case.
Kind of similar, not exactly the same. Like your laptop has a battery, but maybe you need to make a phone call, so you might use your laptop battery to charge your phone battery.
Sure. Okay, so it can also be storage, secondary storage for other operated devices. Yeah, I don't know, it's some sort of a combination of these two which is happening. Okay, good one. So batteries used for a variety of purposes. Okay, what is a battery? Okay, and so when it comes to energy storage, there are many ways you can store energy, and I guess batteries is one of those, but there are others. Actually, what are others? Any thought? What are the other ways we store energy in our electronic systems? Capacitors, okay, big capacitors or dense capacitors. So-called supercapacitors are the one which basically are able to. And there's a lot of cool work happening, in fact, here at UCLA on creating capacitors which can store at energies at densities approaching batteries. Okay, there are other ways also you can store. What else? So if we kind of jump beyond, a little bit beyond just our electronic systems, if we look more broadly, what are the other ways you can think of storing energy? Okay, you said gravity. What did you say? Right. So any form of energy, so thermal, gravitational, they all we can go back and forth. Mechanical. So all of these things exist, and there are companies whose model, like there's a company out of MIT. What they have is essentially huge factory full of centrifuges. Okay, and the energy is being stored in them. So mechanical energy, molten metal, or hot water. These are ways of storing thermal energy. Water stored up in the tank. Okay, these are examples. For tinier devices, they do have mechanical stuff, so like some spinning mass or something like that, or spin mass systems, those kind of stuff which are there. Okay, but the particular one which is most common, obviously, is batteries. And batteries basically are made up of many electrochemical cells, and essentially you're storing electrical energy in form of chemical energy out there. And chemical reactions result in a voltage, so I'm sure you have seen in some shape and form. Long ago in Italy, it was the first chemical cell. So a cell is made of two half cells, and each half cell is a electrolyte and an electrode, and then you kind of connect them together, so the two electrolytes are connected, and you kind of close the circuit. For our purposes, one of the distinction that matters is whether it's a primary battery or a secondary battery. So primary battery are non-rechargeable, so these are good double A's and stuff like that, and then like alkaline double A. Secondary batteries are the one where the chemical reaction is reversible. So lithium ion, for example, being an example. just yesterday, I think I read a news article that a group at Stanford is claiming that they have finally managed to get a new type of battery which people have been trying, aluminum ion working, which has interesting characteristic that it can be recharged in what minute, 1.5 minutes or something like that, very rapid recharge. Anyway, so I guess innovation still quite a bit happening. Okay, so secondary batteries chemical reaction is reversible. When it comes to battery characteristics, so I guess a very high-level view is battery has certain number of joules, but unfortunately that leaves a lot of suboptimality in the way you would operate the battery. So important characteristics of the battery include how much energy per unit volume or per unit mass it stores, how much power per unit liter or per unit mass it stores. Power is important in some applications where you need to supply a lot of current. So like for example, anything which is a motor and all will draw a lot of current. So those kind of applications, or where there is a sudden like a camera flash and all. Open circuit voltage refers to what is the voltage when the circuit is open. Cutoff voltage, that is what voltage is the battery dead at. Shelf life, which is I buy the battery today, whatever, freshly manufactured battery, how long before it becomes useless. Okay. Cycle life refers to how many times can I recharge a rechargeable battery. So it's only for secondary batteries. All of these are really a function of the chemistry of the battery. So advances in materials and all have always been changing these things, and like I said, even now newer chemistries are being kind of explored. Lithium battery, which is the chemistry which is most commonly currently used, is called lithium batteries because it uses lithium or some compound of it as part of the electrode structure. There are many variations on the basic lithium stuff. So lithium ion is what we use, but there are pure lithium batteries. There are also other lithium phosphate and things like that which are kind of out there also. So there are a variety of these chemistries out there. Some of them are some of the basic lithium cells are actually primary cells. So they are used in like smoke detectors and stuff like that because they have long shelf lives. Okay, or they're used in like sensors which are part of your security systems and all. Lithium ion, on the other hand, which is used in our laptops and all, is secondary batteries because it's rechargeable. So certain battery chemistries out there. So good old days, lead acid and things like that. Nowadays, it's lithium ion. There's another non-rechargeable battery, lithium hydrochloride, which is used quite a bit. The interesting metric for us is, and it kind of explains why the transition happened. So if you look at watt hour per kilogram. Okay, so watt hour is a unit of energy. So energy per kilogram. So lead acid was 41, carbon, zinc, which was before alkaline. These are out here. Lithium ion, which is rechargeable, is out here. Lithium hydrochloride is 700. So joules per kg number. Or we can look at terms of volume. In some applications, the volume matters. Okay, for example, batteries which are used in cochlear implants or whatever stuff people put in their ears, or implantables and all, they're pacemaker, things like that. There one would imagine that it's the volume density which kind of plays a huge role also. So very broadly then, rechargeable, non-rechargeable, and within that what the energy density is, both in terms of mass and volume, and what the current density is, which I don't have out here, but actually one of the reasons nickel cad or NiCads remained around for a long while is in applications such as remote control cars and all, because NiCads have very good power density. That is, they can give out a lot of high current basically. So it took a time before some of those applications migrated. When we look at our typical AA sized cell, you would see sort of a few differences out here. So firstly, how much energy they can store. Okay, so like if you look at alkaline AA, it's 2.6 joules. This is around 3 joules. But the other difference also is voltage. So this was the point I was making in a question earlier also. So alkalines and all are 1.3 volts or so, but lithium is 3.6. Okay, so what advantage do you think that offers? I mean, the fact that lithium ion has 3.6 versus these guys have 1.2, would that affect any aspect of your system design?
One lithium battery instead of like
Three in a series, right? I mean, so it affects the size of your design, right? The volume of the packaging that you have. So those things end up kind of making a difference also. Okay, so one of the more recent innovations in batteries is something called thin film batteries. And kind of the idea in thin film batteries is that we actually put batteries on the same substrate on which we make the electronics. So essentially, we have silicon substrate, and we kind of build up a battery on it. So literally, you have chips where circuit is there, and right next to it, the battery is there on the chip. And these again can be rechargeable. So this kind of gives rise to some interesting possibilities, like you can have distributed batteries, you can have battery right next to the processor acting as a little buffer. All those kind of cool stuff can be done, and they're obviously very tiny. So size-wise, they have a big advantage. Okay. So a lot of cool work happening in sort of batteries in multiple dimensions. There is also nuclear microbatteries, which have been around for a long while. So what these guys do is that they basically consist of some radioisotopes, and they look at the charged particles which are coming out as a result of the nuclear reaction which is going on, and they are used in a variety of different ways, but particularly they are used in applications where replacing batteries is going to be hard, and therefore you want really long replacement time. So for example, satellites or underwater or things like that, okay, are being used. There's some pretty cool work happening in this space. There are also radioactive thin film batteries, so kind of combination with the previous one that we had. Some of the ideas, so this is work out of Cornell. What they do is the radioactive material, the particles coming out of it, they hit a little cantilever beam which is made on the silicon chip, and that gives the energy, which is then used to, for driving the electronics. Main thing is that these things can have lives of hundreds of years potentially. Okay, so they are used in settings where you just want these things to be last. Finally, before we turn into modeling batteries, so as of a few years ago, lithium iron phosphate batteries were the fastest charging batteries out there, or fastest charging and discharging. So in 10 to 20 seconds, they can fully discharge and discharge. Supercapacitors are the next best thing. Supercapacitors we can charge very rapidly. As of 2013, the largest battery was in China, $500 million, 36 megawatt hour. Obviously not for our cell phones, it's for grid. Other large batteries is stuff in Alaska and so on and so forth. So there are these huge banks of batteries and all. And one of in case of power grid, the electrical grid, one of the things is that if we can kind of have cost-effective batteries, then essentially renewable energy becomes a very attractive proposition. That's kind of a show-stopping thing. Okay, so that's the state of batteries. The thing I want to focus on is how do we model the battery behavior, and what does it mean for us in terms of how we manage rest of the system. So theoretical capacity of a battery is basically the amount of chemical it has, because ultimately if we are going to convert that chemical into electrical energy, then that's what we have to play with. So a first cut model of a battery would be that it's the bucket of some amount of energy. So what that model would yield is the following. So let's say if I were to tell you that I have a processor hooked up to this battery, and let's imagine the processor has no leakage current. Okay, so hypothetically, and I halve the frequency of the processor, then I'm halving the power of the processor, and therefore the current draw out of the battery would be half, and therefore the battery will last twice as long. Okay, that would be the model, right? Because for processor to consume the amount of joules the battery had, it will take twice the time, so that would match out. So halving the power by halving the clock frequency will double the computation time, but will maintain a constant amount of work we can do before the battery dies. Unfortunately, batteries do not work that way, and the reason is that batteries, in reality, the amount of energy they can deliver depend upon how we discharge the battery. So what I mean by that is that if I have a battery and I draw energy from it at some rate x versus I draw at some rate alpha x, then the battery life will not change by the factor of alpha, but by some different factor. And the factors that matter out there is what is the rate, what is the profile, that is, am I drawing the current out at a constant, or am I kind of bursting things like run the battery for a while, let it sleep, run the battery for a while, let it sleep, so let it relax. And then finally also the power level and all to which we have drained it. So in case of rechargeables, if we deep discharge the battery versus if I shallow discharge the battery, all of them have ramifications. So battery capacity, if you look at like its data sheets and all, it's not a constant number. It's usually given as a plot like this, where what it will show is that for different discharge rate, it would have a certain battery capacity. Okay? So this is capturing the fact that rate matters. And the rate in case of batteries are quoted in terms of some C's. So 1C, 2C, half C. And the C depends upon what the battery is. Okay, so it's kind of like for a battery, C may be 1 ampere. So in which case 1C would be 1 ampere, 2C would be 2 ampere. So it's normalized to this. I'll sort of come to that what it means. But the capacity printed on the battery is usually the product of 20 hours multiplied by the constant current that a battery can supply for 20 hours at 68 degree Fahrenheit down to a specified terminal voltage. So so if a battery says that it's a 100 ampere hour battery, what that means is that it will deliver 5 amp over a 20-hour period. Okay, so you divide this thing by 20. So that's because that's the hour part. So it's basically saying that it will deliver 5 amp over a 20-hour period at a room temperature. Okay, but if I take the same battery and actually take 50 amp current out of it, then its capacity is not going to be 100 amp hour, but it will be lower because we would be on the right. So they're giving you one of the points out here, and if I'm discharging at the higher rate, it would be something more. So the discharge rate matters, okay? And again, the capacity that they're quoting is for the 20-hour period, okay? So when you see like somewhere I had these numbers out here like this one. So like an alkaline long life is basically saying that it is 2122 milliamp hour, okay? So we'll divide it by divided by 20, and that will tell me what current we are looking at. So this guy can give me 20 hour of lifetime when operating at 106 milliamp. Okay, so that's the interpretation that one has to attach to this. Okay, so battery discharge rate is can also be specified in terms of the C ratings. So for example, a C over 10 rate for a 200 amp hour battery will be 200 divided by 10 amp or equal to 20 amp. Okay. So it depends upon this. The other thing it depends upon is the following. So what you see right inside is time and voltage. And let's say I am drawing current out of the battery and I monitor how the voltage is changing. So as I draw more and more charge out of it, the voltage will drop, and at some point we will declare the battery to be dead. But let's say instead of doing that, what we do is we discharge it for a while, so we follow the same curve, but we stop. Then in a short while, the voltage will jump up. This is called relaxation. And then again we discharge, so now the voltage will follow this other curve, and then again we stop. And then again the voltage jumps up, and then again same story. Okay, so we stop for a while, we let the voltage jump up, and this way we essentially stretch out how long we can operate the battery. So this property is, so essentially what we're saying is the following, that if I keep discharging the battery on a continuous trend, then I will get fewer joules out of it than if I were to stop for a while, let it relax, again do the same thing. What do you think might be happening? Like what cause? And I'm sure you have seen this phenomenon, right? I mean, your flashlight dies, you let it turn it off for a while, turn it on again, it works for a while, right? So that's exactly what is happening out here. But why do you think it happens under the hood?
Heat.
No.
It's chemical.
Huh?
It's about the chemical.
Yeah, it is about the chemicals. So what about the chemical?
Does it like get mixed more evenly?
Yeah. So essentially, yeah. So your intuition is right. Okay. So this is what happens, right? I mean, essentially, what's happening is inside the electrolyte are ions. They are moving, right? But they have mass, so they are sluggish. So what happens is, what matters to me, what matters in the battery, insofar as the voltage is concerned, is what the concentration of these ions is near the electrode. But since those ions have mass, so the concentration, if I'm continually drawing the current, what's happening is that the concentration near the electrode drops. So the ions are elsewhere in the battery, but not where I want. So when I stop it, they get a chance to evenly distribute, and then again I can start. So that's basically what happens under the hood. So it's a process of relaxation. What beneficial ways do you think a system can use this property?
You could have multiple batteries and then switch between them.
Okay, so multiple batteries, I can switch between them. In fact, a homework problem I handed out the past couple of years was the following. Let's say I have multiple batteries. Okay, so what strategy is better? One is what you are suggesting, that I operate this battery for a while, let the other idle, then the next one, and kind of repeat it, right? So I'm kind of upset. The other one is out here. If you see here, what it says is that if I operate the battery at a lower current, I get more life out of it also. So I could imagine that I have n batteries, and I operate them simultaneously so that the current is distributed among them. And then each battery, instead of operating here, is kind of operating here. Okay, which one is better, right? I mean, both strategies seem to have some intuitive advantages and all. Okay, so anyway, just throwing that out. So, but what it suggests is that batteries, the underlying battery architecture behind the battery system. Also, you can play all these games. You can switch among batteries. You can gang up batteries in parallel. Batteries in series, we gang up because of what? Why would we put batteries in series? Higher voltage, right? So voltage accounts for batteries in series. Current accounts for battery in parallel. Current and also redundancy, right? If something fails, we still want to keep running. And then finally, these kind of techniques. Okay, so all of this is done. This kind of management and all is done by something which is called battery management system. In simple devices, it's essentially non-existent. But when you look at laptop type stuff or cameras and all, it gets more sophisticated. And by the time you're looking at something like an electric vehicle, it is really complicated. Okay, that's all sort of. It's essentially a control system. It has at its disposal a bunch of batteries, and it has to come up with an optimum policy of how to extract energy out of it. And furthermore, you can imagine that the rest of the system can work in concert with it. So, for example, I could also, if I didn't have multiple batteries, so kind of building further upon your answer, if I didn't have multiple batteries, what I could do is to arrange for my protocol or my OS to kind of shut things down at those junctures, just to give the battery a time to relax. Okay, maybe that's an option. So people have explored these kind of ideas over the years quite a bit. One thing which has changed is that not every battery exhibits these effects to the same degree. So this is again chemistry dependent. Some batteries have a somewhat flatter thing, and also some battery chemistries do not see that much of a relaxation property out here. Okay. And of course, the other thing is that I may have a very mismatched system. Like you might imagine that if I were to take a, I don't know, like a our battery and run a embed on it, it's probably not going to have much effect. Okay, I mean, all these effects are going to be invisible. The range of power that embed can draw is a tiny blip out here. Okay. On the other hand, if I take a AA battery and try to run a huge device on it, okay, then we'll be in the other extreme. Okay, so the relative match between the load and the battery kind of also matters. But the two key takeaway points out here are: number one, how much juice you get out of the battery depends upon the rate at which you are discharging, and the second thing is it depends upon this temporal behavior, this relaxation effect that happens. And what that leads to then is that one has to somehow, like, since again we are after modeling, so somehow we need to have a way to model these effects. So to summarize this part then so we have the issue of battery capacity versus discharge current kind of plays out in these two ways. That amount of energy delivered is decreased as the current is increased. Okay, and at high currents, since the underlying diffusion process, the movement of the ions cannot keep pace with the rate at which I'm drawing the current. So what happens is that even though there is still chemicals left in the battery, it will appear as if we have run out of it because it's not near the electrode, and therefore if we let the battery relax, the battery kind of revives. Okay. There's another thing to also realize is the following, that batteries self-discharge. What that means is that if the battery is just in the circuit, but the circuit is not drawing any current, the battery is still leaking, okay, because the chemical processes are still going on at a slow rate. So unfortunately, what this means is, if you don't use a battery, it's kind of the leakage power consumption counterpart out here. If I don't use the battery, it's going to leak away anyway. And the leakage current, again, is depends upon the battery chemistry and all, and particular, I mean, we see this stuff with our like laptops and these kind of things. Also, the rechargeable batteries leak away. Okay, so if you don't use it, it's not as if that energy is available for you. It's just going waste. Okay, so there are several things at play out here, right? I mean, one is our ability to extract depends upon these two factors. The other is, in case of rechargeable batteries, when we put energy into the battery, we are not going to get all of it out, okay? Because the recharging circuit and all are going to have inefficiencies. And the final part is, if I put the energy now, and if I wait some time before I extract the energy, I will have a time-dependent loss which will happen, okay? So these are losses in the circuit, so one has to factor that in also in terms of one's strategy. What do you think leak more, battery or capacitors?
Does the leakage depend on the amount of time? Like, does it leak more if it's
Sure. I mean, leakage is a current, right? So what's happening, you can, to the first order, you can model it as it's leaking at a particular rate. Okay, the leakage current is going to depend upon the voltage. It will depend upon the current state of the battery, but there's basically some leakage current. So yes, you integrate that over time to say how much energy we have lost. Okay. Huh? Yeah, capacitors leak more. Unless you cut them off from the circuit totally. Okay, so capacitor. How do you think capacitor and battery stack up in various dimensions? What are the pros of capacitor and what are the pros of battery, or whatever relative pros? So who stores more energy per unit mass or per unit volume?
batteries?
Batteries. No. Okay. What about their ability to supply current? Capacitor, which is why we use them in the flash. Okay. Leakage, we talked about capacitor are worse. That's okay. What about recharging? Yeah, so capacitors are inherently rechargeable. Okay, and more importantly, capacitors capacitors have much longer cycle life. Cycle life refers to how many times can I discharge them. Okay, so capacitors are very good on that dimension. Improvements in capacitors are taking place, so they are creeping up to the battery territory when it comes to the energy that they can store. So someday perhaps they will take over and we won't need batteries. Capacitors are also cleaner because there's no like heavy metal or whatever, lithium ion, these sort of dangerous chemicals involved. So they are kind of nice. In fact, a lot of capacitor work is making use of things like carbon nanotubes, graphene, and things like that. So that's how they're kind of storing large amounts of energy. So in any case, upshot of all of this is that how we discharge from the battery matters. So the very first attempt of, so we started out with kind of the crudest model. Battery is a bucket of k joules, and we now realize that that doesn't work. So then the next up is the so-called Puchert's formula, which basically captures one of these effects, which basically gives us the battery capacity as a function of current. And very crude, there are many variants of it. If you look at Wikipedia, it has kind of a slightly different formula, but it basically looks like the following: the capacity of a battery, the charge capacity of the battery, is equal to some constant divided by I to the power alpha, where I is the current. So basically, so Cp depends on the chemistry in the design. Alpha is 0 for an ideal battery. So in an ideal battery, there is no current dependence. So capacity is equal to some constant. But since alpha is non-zero, so this kicks in, and as you can see, what will happen now is that alpha usually is like 0.5, 0.7, something like that. So what will now happen is as the current goes up, the denominator will go up, and therefore the capacity will go down. Okay, so that's basically, so it's a good first order approximation, but it does not capture a relaxation effect. So there are, like I said, some twists on this basic concept. So assume that the current is an ampere and capacity is an ampere hour. Okay? Then Cp is capacity in ampere hour at discharge rate of 1 ampere. Okay, so that follows, right? If I is an ampere, Cp is an ampere hour, then I equal to 1 means C is equal to Cp. So therefore, Cp is nothing but the capacity when the discharge current was 1 ampere. Let L be the lifetime for the at current I in ampere, then plugging it in, L is going to be equal to capacity divided by the current. Just plug it in, so I end up with that Cp is equal to L multiplied by I to the power 1 plus alpha. Okay. This equation one has to make sure that you're getting the units right, because we have this to the power alpha. It's very clear. Okay. So in case of Wikipedia article, what they do is they present the formula in this way: Cp is equal to T, which is the lifetime, multiplied by I to the power beta, and they call beta to be Puchert constant. And in this case, beta is 1 for ideal battery. So sometimes alpha is used as a Puchert constant, sometimes this 1 plus alpha or beta is used as a Puchert constant. So anyway, so sort of like this. In case of electric batteries which are used in electric vehicles, this rate capacity effect becomes kind of an important aspect, because there is a significant sort of variation in the current that you draw, and that can affect things quite significantly. In electric vehicles also, the voltages are much higher, so the battery packs are rated for 48 volt or something like that, so they have lots of cells in series. They use the same lithium ion cells that we use in our laptops, but just a more gigantic sort of pack made of that, and they use many of them parallel so that they minimize the effect that we see because of this rate capacity effect. So alternative representation of Puchert's law is that in this form, Cp is I to the power kT, and that's what sort of Wikipedia uses. Okay, so yeah, I just wanted to bring that out. Now, usually we do not know the capacity at the 1 ampere discharge rate. So when you look at the data sheet, they usually do not give you the capacity at that rate. So say instead we are given the capacity at some rated current. Okay, so recall I mentioned that battery capacity is rated. Usually, like the data sheet will give you a rated battery capacity in ampere hour, and that will correspond to the 20-hour thing. So that is the current corresponds to whatever it would take for 20 hours. So we are usually not given this. So you have to always kind of reformulate things a little bit. So if I'm given a battery capacity C rated in ampere hour and corresponding discharge time is L rated in hours, it's 20 hours normally, and then you can, and then the battery is actually being discharged at IAC, you can work things out and essentially come up with an effective capacity. I'm not going to walk through this, but point is that to apply the Pucher's formula, you have to take that rated capacity which is given, which is usually given for a 20-hour lifetime, convert them into a current, feed it back into this formula, because what you need is CP is that constant corresponding to 1 ampere discharge time. So some algebra needs to be done to apply the Pucher's formula. Another way Pucher's formula sometimes is another way that this effect is seen is the effect of these batteries by just plotting them on something called Ragone plots. Okay, so these are used to compare batteries in a somewhat different dimension. So on x-axis we have power density, and on the y-axis we have the energy density. And what we are plotting out here is that how batteries do in terms of these two dimensions. Okay, so ultracapacitors or supercapacitors are very high in power density, but they're kind of mediocre when it comes to energy density. Conventional capacitors, again, very high in power density, but they're pretty bad in energy density. So that means that for same amount of storage, they'll need to be much bigger. Our batteries tend to be up here, which is they are very good in energy density, but they are not as good in power density. And fuel cells, which are not a battery technically, okay, these guys are really very good in terms of energy density and worse off in power density. So this is kind of a good way of visualizing things. And again, ideally, we'll want a battery pack which sits out here. And the work which is happening in capacitors and all is really seeking to push this guy up here. And someday maybe like Back to the Future movie had this flux capacitor, which is kind of like up here, I guess, conceptually. So kind of the goal is to make capacitors basically take over the batteries. Okay, that's what's happening. Yeah.
How would you make the battery go to the right?
Trickier. I mean, so actually, the aluminum ion battery seems to be doing that. Okay. I did not read the actual article other than the news story. I don't know. Did you read the article? Like, what have they done? The aluminum ion one. Yeah, the one which came. Yeah, I mean, I just saw the news blur when they had a link to Stanford researchers say something, and then I never followed it up. Okay, but that's an example. I've also seen some other things, like I don't know how. So like the newer Samsung phones, the S6, they are claiming one of the things being that they can very rapidly charge to the 50% point, but I suspect, I mean, it's not a new battery, but I think they're playing games with how the battery is charged. So actually the way these batteries are charged itself, I'm looking at the discharge story here only, but the way the batteries are charged is a tricky one. Yeah.
There's also a recent work here at UCLA on graphene battery.
Right, I was mentioning that. So that's this one. It's not graphene battery. It's capacitors which are getting into battery territory. And I guess they are looking into some sort of capacitor battery hybrids. So part of the idea is you can kind of combine both of these things together. Okay. So it's like Professor Bruce Dunn in chemical engineering and Craner or something like that, right? Yeah, he in chemistry. They are kind of doing. They've been in news quite a bit on that work. So so someday this corner will get occupied, but not anytime soon. Fuel cells are essentially, one way of thinking about them is they are batteries with replaceable electrolytes. Okay, I mean, it's not quite the same. They don't work the same principle as rest of the batteries, but that's the way of thinking about it. The idea is that the way you recharge them is to essentially buy some, like if they're methane based, then there's some sort of a module with methane, liquid methane or whatever, you plug it in. So you refuel them. Okay, that's kind of the concept. whereas batteries we replace by replacing kind of the whole battery. Anyway, one of the videos I had seen for electric vehicles was this is an Israeli company who came up with, but then I think Tesla has bought them or whatever. So kind of the idea is that instead of recharging the battery, you replace the battery robotically. So you kind of your car pulls in, and there's a robotic mechanism comes, swaps the battery, and what they show is that it can swap the battery and all much quicker than you can fuel your car using a gas pump. So the deal that Tesla offers in those places is the following: if you recharge, namely which takes around an hour or so with the fast charger, then the charging is free. If you use the robotic mechanism to replace the battery, then you have to pay whatever is the local price for a full tank of gas, basically. So that's kind of the model. So one of the things of interest to us then becomes the amount of computation that one can do during the battery lifetime. So there are two terms that you are going to see which are misleadingly close. And I ran into trouble with them in a conference recently where we were reviewing the papers and all. But anyway, there is something called battery life and there's something called battery lifetime. Okay, and also depending upon whether you are a computer science person or whether you are a material science person, they kind of get used mixed in. Okay, so one notion of life or lifetime is that I charge the battery or whatever I bought a freshly charged battery. How long will it be before I will run out of juice? And the other one is how long it before the battery becomes unusable. So like I've been using the battery in my laptop and at some point it will stop holding the charge, electric charge. So in computer science, since much of the work has focused on the issue of how much computation I can do before the battery dies, so the lifetime is usually used to that how much time before, like if I'm doing some workload, what's the lifetime of my cell phone battery, a day or whatever, right? I mean, they look at it in that terms. Whereas when you look at the literature, which is from the battery community, from the chemical material side, they use the same terms to refer to that how many charge discharge cycles can take place and all, and before the battery becomes useless. Okay, and these are two obviously very different notions. And I think since not much work has happened in computer science side of things, on only now models for the latter have begun to emerge. That there are sometimes papers you will see which we call things battery life or lifetime, but they may be different to different things. Generally speaking, battery lifetime is for the single charge. Battery life is when the battery's life is over. Okay, just wanted to mention that. So, going back out here with Fuker's formula, let's imagine that I make some change to our system so that it changes the system performance by factor of n and it changes the power by a factor of x. So what will happen now is, so I play some trick, maybe voltage scaling, frequency scaling, something like that. The net result of that change that I made to the system is that its performance went changed by factor of n and its power consumption changed by factor of x. So the total work that the system can do before the battery is exhausted, since the current went up by factor of x, so it will basically, the lifetime total work will change by n times x or minus 1 plus alpha, because the alpha would come into play. If battery was ideal, then alpha was 0, and therefore the work will change by n over x, okay, because my speed went up by n, but my power consumption changed by x, so the total ideal battery would be n over x. But with a non-ideal battery, a battery with following Fuker's law, it would look like this. So, for example, let's say I reduce the clock frequency by a factor of n. That will reduce the power by factor of n, and it will reduce the performance by factor of n. And I combine these things together, I will say the work done before the battery dies changes by n to the power alpha. In an ideal battery, alpha is 0, so this would be 1. So that's what we'd expect. In an ideal battery, If I slow the processor down by a certain frequency, and if its power changed by a factor of n, the battery should last the same amount of time, but not if there's non-idealities present. But so what this means is that the work, as I reduce the frequency, because I'm lowering the current, and therefore I'm moving left on that plot, so I can get more energy out of the battery. So the lifetime for the battery appears to have run out of charge increases. So what this suggests is that I'm better off operating at a slower frequency, because I can get more work done before the battery dies. But there are certain things which will prevent this from happening, which the first order model ignores. Firstly, as I keep reducing the frequency, the static power will become to dominate, and therefore power reduces by a factor of n will no longer be true, and so that will become a factor. The other thing which I have not listed out here is, and the battery, there will be more leakage loss in the battery, so that will come into play also. So there's probably going to be, generally speaking, a sweet spot which would be the, if my goal is to maximize the work done before the battery dies, and so there would be a sweet spot in terms of what speed with which I should run the processor, and it would factor in these kinds of effects. So there will be some sort of a maximum computation, but you'll need to know battery life, whatever, battery's model and the processor's model to be able to sort of come up with that as well. So running very rapidly may not be a good idea. Okay. I guess in cases like electric vehicles and all, what it will translate into is if you drive your Tesla at the peak speed limit of whatever it has, 200 miles per hour, you'll run out, you'll go shorter distance. If you drive your Tesla very slowly, you'll not travel much. There will be some sort of a sweet spot where you maximize the range. Okay, and it's the same concept applies here for computers as well. Okay, there's a sweet spot at which you will get most out of it. Now, the question remains. Our devices tend to have a mixed kind of thing. If you think about your phone, I guess for some applications, we care about how long they last. Whereas for other applications, we care about performance, and the overall device is somewhere kind of in the middle. Okay, so it's sort of, our devices are not single purpose, so that kind of complicates this picture a little bit. Okay, let's see. Let's stop here. I'm not going to start on the pulse discharge today. It's going to take longer than 10 minutes. But the next model up that I want to go up is how do we begin to model the other effect which we ignored. Another thing I would mention is the following, that there exist battery models from the chemical engineering, chemistry folks. And these are models which are essentially modeling the chemical phenomenon, okay, the chemical reactions. And so there are some very well-known models for that. The one which is used quite a bit is a model which came out of Berkeley. It's something that a lot of us in computer science have played with. It's massive amounts of Fortran code. It is some, if I recall right, 39 differential PDEs, partial differential equations, couple PDEs with some close to 100 parameters, and that's your battery model. Super accurate, does very well. More recently, there have been models which capture other aspects. What's the voltage of the battery? What is the capacity? Because in many apps, voltage matters, as well as what is the cycle life of the battery. That is how the battery ages. In computing side of the story, unfortunately, those models are not very useful directly. That is way too complicated. So things like Pucher's formula, or we are going to see next time around something called Rakamatov model. Okay, these are attempts at coming up with compact models which are computationally better and easier for us to deal with, and which we can use during our design process. So let's pick up the thread next time around. Someone sent me an email about the lecture recording, so I sort of converting them, and they should be up later today. So.
Are the lecture slides?
Lecture slide. Other than the battery one, all of them are already on Piazza. This one, I'm.
I only see the first one on Piazza.
Huh?
I only see the very first set.
You only see the very first set. Okay, I'll go and fix it now.